So I'm really sorry not to be able to be there because I've never been there, and I would like to. I'll try to find a way to visit. I realized the title that I gave myself is a bit too generic, and I cannot really talk about everything. And since this is a magnetism and accretion conference, I'm going to talk mostly about neutron star QPOs. That's something that was sort of left dormant for years, but it's important to remember where we stand, and we do have some new results. Since I chose that title, I will show that the first QPO in an X-ray binary was actually discovered 40 years ago, in 1983. It's on the left. There's a QPO in the optical and in the X-rays of GX39-4. And there's the first reported detection of something that was actually called a QPO as well. And on the right panel, you can see a more recent detection with NICER, work that I'm writing up right now. It's a different system, but you can see that the quality of the data, of course, has increased considerably since the times of Exosat. That was, I think, 1983. These are black holes, but for now we are left without ROSI-XTE. This is my usual slide that shows that ROSI-XTE was perfect. It had a large area, the good energies, and a fantastic strategy. Now we have essentially three missions: Astrosat, NICER, and HXMT, and all of them are missing something to have exactly what we had with ROSI-XTE. But we shouldn't despair because they have very good properties, and they can be used even alone or together to find answers. Now, for neutron stars, in the distant past, the first QPOs that were detected were interpreted in a model that kept into account that there was a rotating neutron star with a magnetic field, the so-called beat frequency model, because the field just had to be involved, and the rotation of the pulsar had to be involved to give these very fast oscillations. But then it turned out, after quite many years, that this model doesn't actually work. And people have tried to look for different explanations. And the model that came up at the end of the 90s was the relativistic precession model by Stella and Vietri, which identified the three peaks that you see often in the power spectra as three fundamental frequencies from general relativity. You can see the plot with the power spectra has two red arrows. Two of these are, there's a third peak. There are three peaks, and one of them is the orbital time scale. One of them is the precession of the elliptical orbit, and the other one is a precession of length steering around the neutron star. And it worked pretty well, not perfectly, but decently well. If you take the red lines, the red arrows, and you plot those numbers, then you get that plot by Ford 1998, where you can see that the model fits with the right slope. Not exactly the right normalization, but the right slope. Problem is, there were no more data after XTE. There are no more detections of these high frequency oscillations, so it's difficult to go forward. And we had a lot of data before as well. At those times, we also found this very wide range correlation between oscillations. I don't want to describe this too much because that would take too much time, but this plot contains three different types of points: the narrow peaks in blue, the broad components in red, and the spurious peaks in magenta. Spurious meaning some of them don't exist, some of them should not be on this plot. The beauty is that the model works even without modification. So nobody ever made this plot, but if you actually make this plot with the model, it is explained. So that was very good. And then the other interesting plot related to this model was this one, where you plot the difference between the two high frequency oscillations and the upper one of the two. And these are the points, not that many points, but then the model for a certain mass, which is essentially the only parameter, is shown there. I don't know what the mass is there. But it's not perfect, but it's kind of there. Like there are high frequency points that are not really there. What we did in the past few years was to collect all published detections of oscillations in the literature and populate this plot. And this is the final plot from ROS-TXT for these kilohertz oscillations. And you can see that there's a lot of scatter. Of course, these are different sources. They don't have to have the same masses. I think the masses are 1.8, 2, and 2.2 solar masses. But there are three predictions made by this plot, by the model. One is that at low frequencies, the points go up, and it does happen. One is that at high frequencies, the point go down, and it happens. But there's a third prediction that nobody ever mentioned, that there has to be a maximum in the y-axis, depending on the mass, of course. And that also is quite nicely seen in the picture. And notice the yellow star. The yellow stars are millisecond pulsars, and they are low by a factor of about 1.5. We'll get back to that. So if you do, on the left, you see the same plot. It's just nu1 versus nu2, no difference. And on the right, you have a distribution of delta nus. And if you look at the total, which is the black, you can see it's kind of Gaussian. It used to fit the Gaussian very well. Now it doesn't. It's actually steeper on the high frequency side, which is okay because there has to be a limit in the delta nus that you can observe, or the upper limit. So there seems to be like this difference is always 300, more or less. And then there's a relation to the spin of the neutron stars. The first one that was found was SAXJ 1808, that was mentioned before. And it's an empty point here. And you can see that it's the y-axis is the difference between the two QPOs divided by the spin. It's 0.5. So you have a spin of 400 hertz, the pulsar was detected, and 0.5 is delta nu divided by 400. So that was fantastic, but then there was another one found. I don't know if it was that one, but I just chose one, and it was about 1. So the model came up that the difference divided by spin is equal to 1 until 400 hertz, or sort of, and then half afterwards. And then people populated this plot, and the points more or less fitted. Delta nus vary, so it's not really exact. Each x value has many y values, but it's kind of, the ones up there are about 1, the ones down there are about 0.5. However, completely different considerations suggested that the observed millisecond pulses were to be increased by 1.5. So they were below in everything by 1.5. So if you put them up by 1.5, this is what you get. And then you can see it in the plot. Nobody ever made this plot before. They just said, oh, it's about 1, it's about 0.5. And then if you look at these points, you can easily imagine a much more natural fit, which is this one, which is constant delta nu equal to 300. It's not a fit. You cannot fit because the points are not consistent with each other. But it's still, this is a completely different consideration, but it suggests that there is a rather constant delta nu at 300 hertz. In 2008, there was a new spin detection at 415 hertz. And once you have a spin for a source, you have a bunch of points to put in this plot. And this is possibly confirmed by a paper last year by Chen et al. And it's a very important one because 415 is right in the middle. And these are the points that you can get out of this detection. None of these points is compatible with 0.5 and 1, but they all cluster around 0.7, whatever, the value which is exactly in the middle. So it looks like the best way to see this is that there is no relation with the spin. How can there be no relation with the spin? You have a very fast rotating neutron star in the system, and there are other things which are, I'm not going to show here, but each source seems to know the spin of it, of the neutron star, but if you take them as a whole, it doesn't seem to know anything. And so this is the main point where we are now. The problem is that we can't really do anything anymore because we don't have any more signals, but it's very good for the future, of course. New missions are being planned or prepared, and we'll have to wait for those really to get new data. There are more advancements now in the black hole binaries, which is what I'm doing and many other people are doing at these times. The important point that I always make is that you cannot ignore fast timing. If you look at these two plots, one is, I have no idea which source, but it's a hard state source, and you see the variability you have there is gigantic, and it does have spectral variability. So you need to take that into account. And the bottom plot is, again, for an unknown source, because I don't remember, a low-frequency QPO in a black hole binary, plotted with a y-axis in a linear way. And you can see that you can hardly ignore this system. It's not a pulsation, but this peak is really gigantic, and you have to explain that. The high-frequency signals I'm not going to talk about here at the moment because they're too faint, and it's not possible to do them now. But if this one, I think, is a nicer power spectrum, although I'm not sure, but you can have very good information. The RPM works well on RXT data, as I will show in a moment. The question is still one of the major ones, is why do we have such beautiful low-frequency peaks in black holes and very poor high-frequency peaks, while for neutron stars, it's the other way around. We have a fantastic database of high-frequency oscillations, and we don't have very good, so good low-frequency oscillations. And in the past years, what I've been doing with colleagues like Sarah Motta was to try to extract a spin of the black hole from the model using the very few cases where you can do that. And it was actually extended to broad components by Bhargava et al. 2022. And you can see here the spins that we get. We have 4 sources. I think this is essentially the maximum we can get to with XTE. We have 4 very accurate values of spins, and in one case, 1655, we also get the mass of the object, and the mass of the object is compatible with the optical mass. Now, the spins are low. If you look at the detections done with iron lines or continuum fitting, they're much, much higher values. They are not really compatible unless there are big errors involved. But they're much more compatible with what is now coming from gravitational wave sources. So I don't say that these ones are true, but these are actually detections that should be taken into account, and they're based on a very simple model, which is actually a bit too simple. It's just relativity. You want to actually have the whole gory details of accretion in there, because the plasma is a complicated thing. And if you see the mesmerizing rotating disk at the bottom, Adam Ingram has developed a model which is a bit more connected to real sources, to reality, which only applies to the low frequency oscillation so far. But that is changing some things. So these numbers might change if you apply that model. But this is advancing. We don't have any more high frequency oscillations, but we can work with the low frequency ones and the noise components. And finally, with QPOs, you can actually go and get accretion geometry. All these oscillations are associated probably to a radius, at least they have been associated to a radius by models. And by applying spectral timing, people can actually go and have a look at the geometry of the system. And this is just an example. The Goplin Groningen has been working on that a lot together with me. And with a very simple feedback model, which has nothing to do with the QPO origin. So it doesn't matter what the origin of the QPO is, but if you have something that starts oscillating, that something else will start oscillating, it will feed back and re-shine the oscillation on the first one, and then you will get something which, as you can see in the plot with the points, which I'm not going to describe because I have no time, it fits pretty well, and then it can give a very good idea of the geometry of the system, as you can see on the plot on the right. And for this, new data are crucial, and as I said, we have 3 very nice missions available. They are not XTE. Do not try to use them as XTE, then you will fail. But if you just concentrate on what's really powerful of these missions, then I think we can go much more forward, waiting for the brand new missions that are coming in the next decades. Thank you.
Thank you, Tomaso.